Continuing on with our engineering analysis and our recent update here on the UPS Flight 2976 crash in Louisville, Kentucky. So yesterday, the NTSB gave us this Aircraft Accident Investigative update. Now, in it, they're showing us some laboratory results that they've been working on over the last couple of months. Let's take a look. So you remember on the last video, we pointed out that as part of the investigation, airport surveillance videos that captured part of the airplane's takeoff roll showed us that the left engine, which is the number one engine, and its pylon separated from the wing right after rotation, which is when the nose lifts up off of the runway. And then, of course, a fire ignited on the left engine and near the area of the left pylon wing attachment, so right where it connects up onto the wing. So in this NTSB materials laboratory exam, they were focusing on the spherical bearing part. And so let me bring you up to speed. And so the way the engine attaches to the pylon on the wing, which I've showed you before, is right here. And on the pylon, these are the 2 points that connect to the wing. See, there's a forward part and there is an aft part. You see how you have like this eye right here? This is a boring hole where the pins go through to attach it to the wing, onto this wing clevis right here. There's 2 lugs, as you can see here in the picture, and then in the blow up, yet they're side by side against each other. There's an aft lug that you see in the green, and there's a forward lug that you see right here on the yellow. And then in the middle is a spherical bearing. And so in here, the bolt goes through here and passes through all 4 sections of metal. And that's how it attaches on the rear. And then in the front part of the pylon right here, there's 2 vertical bore holes. Each has their own spherical bearing as well, with a bolt that goes through that connects it onto the forward wing clevis. And the same thing here, you have bolts that go through there. So this is the 2 main attachment points for your engine pylon. And this is what broke. So here they're showing us what they call an exemplar photo. And this is supposed to be representative of what it would look like in normal airplanes. Your aft lug that I showed you on the drawing before. And then here's the forward lug. And then this big section here and the other section here on the right are the wing clevis. And so the bolt goes through all 4 of these parts and then the nut on the other side. So this is how this whole apparatus connects up. It's a sample one, and this particular sample had fatigue cracks on it also, and that's what they look for. Okay, so this is not the plane that crashed. This is a sample. So this is the aft end of the engine pylon. And so they zoomed into it, and you can see just how badly damaged here that both the forward lug and the aft lug were. So this is the left wing, I believe, flipped upside down, and they're looking at the wing clevis right here. And as I showed you before, right here in the middle of it is where those 2 lugs, the aft lug and the forward lug, were supposed to go. And then this spherical bearing goes right through those 2. And in fact, here's a picture off to the right of what a good spherical bearing is supposed to look like. This thing looks like it sheared itself, it shredded, it just ate itself up. And so here's where the NTSB made this sort of a composite gallery photo to show you how those 3 sections connect together. So here's the 2 broken pieces off of the lug. So see, it should have been one continuous eye round, and then this eye round here is supposed to go right in here, okay, with the spherical bearing passing through it, holding it in place, and then the bolt goes right through here and the nut here. So this right here is your ruined spherical bearing. And then they took all of the parts out and showed us, there's the bearing, and there's the collar there, which is actually called the race. And you could see that it had split itself in half. There's one on the left side of the bearing and one on the right side of the bearing. I imagine they found this part from the scorched crash, and they found this part on the runway. That would be my guess. And it says a special detailed inspection of the left pylon lugs would have been due at 29,000 cycles. So that's way in the future from now, actually. Because if you look, see, there's 21,000 cycles is what's on the plane right now. So that much wasn't really due. However, they did do some maintenance in October where they did some lubrication on it. What's interesting here is that they did do a lubrication task of the pylon thrust links and the pylon spherical bearings on October 18th, just a couple of weeks before the crash. So as you recall, Here's the bearing race that goes around the bearing, and you can see it's split into two pieces now. And they're going to show us in the next picture, this is the view. It's going to be looking down on top of this one here on the forward portion of this bearing race. So they call it a race basically because the bearing sits inside of this kind of grooved area there, and it races around in there. And this is how the loads are transferred, and this is how it sort of gives you a little bit of movement. So in mechanical engineering terms, this race, which is like a collar, is a grooved track that allows a roller or a spherical ball to kind of like hold inside there and to roll around freely, causing minimum amount of friction. Many aircraft structure joints use these spherical rings or ball roller bearings and their attachments to allow controlled movement and load transfer, while letting the structure accommodate thermal expansion, vibration, and shock. So when the NTSB Materials Laboratory was studying these parts, the investigators observed here that the interior surface right here of the bearings race, so there's the arrows pointing to this interior surface that you see right there. It had fracture surfaces, and these fracture surfaces had showed evidence of fatigue cracking originating around the entire circumference at the edge of the design recess groove. So the design recess groove is sort of like in the middle of the piece, and that's where the ball element here sits in it. And so you can see right here, this is where it had sheared. And so this is the fracture surface. And I wish they had given us more close-up shots so that we could have seen like maybe some of the little cracks that had formed along the inner surface here. So the little fatigue cracking that they were seeing there extended through the thickness of the bearing race toward the exterior surface. So they're saying that some of those cracks went all the way from the inside to the outside surface, encompassing about 75% of the fracture surface. If you look at the photograph on the right here, you can see what they were talking about there, because see, the red is fatigue and the yellow is overstress. And so that fatigue is taking up about 75% of the area there. That's what they're talking about. The remaining part of this entire fracture surface, the yellow area, is consistent with overstress failure. So the question we have here then, related to the investigation of how this metal failed, what is the difference between fatigue, metal fatigue, and overstress? They are two different failure modes, but yet they happen at the same time. And this is something that you see quite a bit when you're dealing with, metal fatigue or something, or parts that had fallen apart like this. So the difference is metal fatigue can be thought of as like maybe little flaws, little cracks that develop over time in many places, and they can sort of spread and they can grow in size as well. But overstress is a singular event. It's a one-time event that's catastrophic to the part, and it usually happens when the part can no longer handle the load that it was designed to handle, and so it just snaps, it breaks. One-time event. Now, the investigators said that they did find grease-like material, which I'm assuming is this right here, and possible remnants of this over here, on the spherical bearing assembly. So that is between the ball element and, of course, the bearing race, which you can see right there. So all of this looks to be remnants of grease. Now, here's where it gets a little bit interesting, because Boeing, back in 2011, had warned the aircraft carriers about this particular issue. And they saw this issue 4 different times on 3 different planes. And so they gave some guidelines for how to look for this. So here is how Boeing told the operators to deal with it. And so this is a simplified view of that whole assembly there as the pylon attaches to the wing clevis. And there's the bolt that goes through all 4 components there, right? And so you see this AA line. This is a reference plane for the section AA. So we're going to cut through it, and they're showing us the cross section of it right here. Now, here's the thing. If you're looking at it, this cross section, see this green meat right here, the metal? This right here is the wing clevis. So the wing clevis, that's this big chunky part right here, right? You're looking at the bolt now that goes through everything, all 4 eye holes there. And then the red here is your spherical bearing. There's the ball element. And then the blue here is that collar. It's that spherical bearing race that they call it. You see this right here? And as I showed you earlier, The failure of this blue part here, the spherical bearing race, was that it splits in two, pretty much kind of like down the middle here. And when it splits in two, here's what happens. You notice how right now it's flush with this left edge of the forward lug? And then on the right side, it's also flush with the right edge of this lug right here, the aft lug. And so what happens is when it breaks into two parts, this part here goes to the left, and then this part here goes to the right. And so by doing a visual inspection, you'll easily be able to tell, because when you look up in there into the crack, you should see that these two pieces are in fact flush. And if they are not flush, it means that's the symptom, folks, that your spherical bearing race has broken. And so you need to get that fixed. Now, here's sort of a shocking part here that caught my eye, and I don't know if anybody else has talked about this, but look at this. It says, according to the service letter, a review of the spherical bearing failure by Boeing determined it would not result in a safety of flight condition. And I got to tell you, folks, I have a hard time accepting that, because if this part breaks, what is going to hold your spherical bearing in place? Nothing. It's going to bounce around there and cause more friction, and I think it's going to cause problems and make it fall apart. I disagree with their assessment on this one. Now, here's something else that's kind of interesting that Boeing says in this letter. So Boeing has introduced a brand new part number for this. I guess it's an improved version of this whole bearing assembly. And this eliminates the design recess groove that's on that bearing race that goes around the bearing ball, right? The spherical bearing ball. And so Boeing recommended its installation in the event that an installed spherical bearing is found to be unserviceable. But strangely enough, Boeing does not prevent you from replacing a bad spherical assembly there, that bearing assembly, with an old part number. You don't have to replace it with a new one, which is kind of strange, you know. It's like if they have a new part number, why wouldn't you want to use it? That's always been my saying, right? If there's a new version of your BIOS, why wouldn't you want to update it? So as we look here, they gave us some preliminary flight data recorder information. So this is covering several different parameters that I wanted to show you. That was kind of interesting here. So as you look across time here, this is the whole 30-second flight. This dotted line here is where the engine fire occurs. So when you're looking here at the two radio altitude sensors built onto the plane, it shows that right here at roll-off, it looks like it hit maybe almost 25. I don't think it came back down. It's hard to say, really. Maybe it did, but it looked to me like right here, it peaks around 30 feet. And as I've showed you on the previous videos, it didn't look like the plane got any higher than 30 feet because the wheels hit the top of that warehouse, that UPS storage warehouse, as you recall me showing you that before. And then here you can see the ground speed looks pretty nominal right there. It looks like it got about to 185. So there's nothing wrong with the ground speed here at the rotation where the nose lifts up off the runway. And then here is your pitch up. You normally expect it to be between 10 and 15 degrees. And that was sort of okay. I don't see any problems there. This might be wrong. I just don't know. They did seem to indicate that parameters are no longer reliable after the engine fire. So I'm not sure if it applies to the pitch as well. As you can see, here's your roll. And the roll is, 0, 0, 0. And then right before the plane crashes is when it rotates to 90 degrees. So it rolls over to the left. And then here's your engine N1 and N2 parameters, which go like totally bonkers at the very end here, but they seem sort of nominal here. And now look at this here. So this right here, this I think gives us the most valuable info right here. This is the engine exhaust gas temperature. So if there was a problem before the fire, you would see the EGT spike up right here. This is the dotted line where the engine 1 fire was. But look, there was no spike up here. You see that? So nothing was wrong thermally with any of the 3 engines beforehand. This was strictly caused by the engine falling off. The other 2 engines will then do their normal engine gas temperature increasing as time goes by before it will eventually plateau. So this proves that there was nothing wrong with the engine technically before the engine fell off. It was working fine until, boom, it snapped off. And then here you can see no fire here, and then engine 1 fire indication. The other engines have no engine fire indication here. So it looks to me, I know a lot of people were saying, well, look, it looked like something might have flown into engine 2 and maybe it caught fire. But I guess they will look into that and they will let us know, hopefully on the next update. Now, keep in mind, this is not a final root cause of what caused the crash, because they still don't know why the plane didn't gain altitude. You know, if you lose your number 1 engine, you still have 2 other engines here fully functioning according to this preliminary data. And so they should be able to allow you to increase altitude like this, take off with your plane, go a safe distance, turn around, come back and do your emergency landing. So the NTSB is next going to have to determine for us why that did not happen. They will also have to look into the effects of losing that engine and your airplane handling qualities. What happens? So if you missed the 2 previous videos that I did on this crash, I'm like, what? Are you nuts? You missed it? Come on, get over there and watch those 2 videos right there. Thanks for joining us tonight, and we will see you on the next one.